Um, in this video, we'll look at the attention nodes and caching nodes. Later, we'll also look at some memory management nodes. The video is for beginners trying to understand nodes and its basic functionalities. So there are no fancy workflows shown or shared in this video. I'm using the same workflow we saw previously, where the conditioning node accepts the first and last frames, along with the first and last frame to video model. And these are the nodes we'll be looking at, along with the cache node. The group of nodes on the left, chained one after another, are the different attention nodes used to speed up video generation. Let's first get a basic understanding of what attention calculation actually is. Think of it as a mechanism that lets the model answer a question. Let's say, for this piece of information, which other pieces of information should I pay attention to, and by how much? In a diffusion model, this happens inside the neural network, often many times during every denoising step. Imagine the prompt is a red car parked beside a blue house. The model represents the input words, or parts of words, as tokens. It then creates numerical representations for these tokens. Inside the model, it has representations for many pieces of information. So in our example, when processing car, attention allows the model to determine that the car and the color red are strongly related because red describes the car. The car and the word parked are also related because parked describes the state of the car. The car and the word house are somewhat related because the car is parked beside the house. But the word blue is less relevant to the car because blue describes the house, not the car. This relation is not simply based on the existence of words inside the model. The model learns relationships based on the context. Attention essentially helps the model create relationships between different pieces of information and determine which ones are more relevant to each other. So that was the idea of attention. And now let's look at how attention is actually calculated. A standard attention mechanism creates three things: query, key, and value. You can think of them like this. Query, what information am I looking for? Key, what information do I have? Value, here's the actual information. The model then calculates how strongly each query matches each key. For example, when processing the token car, its query can be compared against the keys of the other tokens. If the query for car has a strong match with the key associated with red, the model assigns a higher attention weight to it. So, in simple terms, the model compares queries against keys, figures out which information is relevant, and then uses the attention weights to combine the values and produce the output. Now, why is this calculation so hardware expensive? The attention calculation happens inside the neural network, specifically inside the attention layers. We know that a token is a unit of information that the neural network processes. So if we have n tokens, the model needs to compare the query of each token against the keys of the other tokens. This creates an n times n attention matrix. In this example, 4 tokens will be 4 times 4 equals 16 comparisons. 100 tokens will be 100 times 100 equals 10,000 comparisons. 1,000 tokens will be 1,000 times 1,000 equals 100,000 comparisons. The attention weights we saw earlier tell the model how strongly each token should relate to the other tokens. And the number of tokens I showed in this example is very small compared to the number of tokens that can be involved in diffusion models, particularly when you're dealing with high-resolution images or video. That's one reason why attention can consume a tremendous amount of VRAM, memory bandwidth, and computation time. So now we know that attention allows the model to determine how strongly each token should relate to the other tokens using these matrix calculations. In a standard attention, these calculations can be performed using relatively high precision data types such as FP16 or BF16. The original Sage Attention uses INT8 quantization for the Q and K calculation, while keeping the other calculation in FP16. Sage Attention 2 goes even further. It uses INT4 for the Q and K matrices and FP8 for other calculations. The modern GPUs we use are designed to perform a very large number of low-precision operations per second, and Sage Attention takes advantage of this hardware capability to accelerate the attention calculation. The Patch Sage Attention KJ and the MiniMax H3, MEM-EF, Sage Attention patch operate in the same general area. However, the MiniMax H3 patch is specifically designed for the native MiniMax H3 model, while Patch Sage Attention KJ is a general-purpose Sage Attention patch. You can choose the Sage backend or precision mode manually, or keep it at auto. The Allow Compile option has currently no effect, so you can leave it as it is. Should we use both Sage nodes in a single workflow? Usually, no. The H3 specific node is the more targeted choice for the MiniMax H3 model. The generic node above can be used with other models with an option to select the Sage backend manually. Sole Attention is different from the two nodes above. Instead of calculating every token-to-token relationship, Sole Attention keeps the most important groups of relationships and skips many less important ones. We can refer to this by calling approximate sparse attention method. So, sparse attention can produce a larger speed improvement, but it has a greater possibility of changing the denoising path if the settings are high. The input fields in this node can be explained, but this will make the video way more boring, if it has been. Still, we can look at a few of the options. The dense blocks option keeps the specified transformer blocks fully dense. This means the sparse attention method we just discussed will not be applied to these blocks. In a normal transformer model, the first and the last few blocks are often important, so you can specify them by giving a range of 0 and 2 for the first few blocks and -1 for the last block. For the MiniMax H3 model, these are the recommended blocks, so these important layers will remain fully accurate. The start and end percentages define when Sole Attention is allowed during the denoising process. We keep the early and final parts of the denoising process dense for stability and use sparse attention only in the middle. The percentages here refer to the total number of sampling steps, so don't confuse them with the video duration or the total number of frames being generated. Another option we can look at is the tau value. A higher tau means more aggressive sparsification, which can potentially make the generation faster. A lower tau means less sparsification, which can preserve more accuracy but increases the processing time. Similar to this, we have tau profile, which accepts a value in string or text format. This value should contain a range of blocks and its corresponding tau value. The tau value we saw below is a single sparsity setting applied to all the blocks. Tau profile allows us to tune that setting block by block. Sensitive blocks can use a lower tau, while more robust blocks can use a higher tau for greater speed. Unlike dense blocks, tau profile does not turn off sparsity for the mentioned blocks, but it allows how aggressively sparsification is applied to each block.
Not yet!
Next, there are 4 caching nodes, out of which one has been uninstalled because it was causing problems. These caching nodes avoid recalculating parts of the model when the current step is similar enough to a previous step and reuses an approximation which affects the final result. A caching node such as Easy Cache is the simplest general-purpose cache, so it should be used with fairly conservative settings, such as 0.1 or 0.15 for the reuse threshold. The setting below can be 0.2 and 0.9 for the start and end percentage. I do not recommend using these caching nodes with a Turbo LoRa. It doesn't make much sense, and it can also degrade the result when you're working with a workflow using only 6 or 8 sampling steps. The verbose option prints some details like how many steps were skipped, and it does not affect the result. So the Easy Cache uses a subsampled comparison and reuses a cached residual, but the Spectrum Cache node works differently. It doesn't simply reuse the previous residual. Instead, it runs several real H3 steps, fits a forecasting model, and then predicts selected future steps without running every transformer block. This will need a separate video to explain properly. Spectrum Cache can skip a substantial number of transformer evaluations, but the documentation warns about bad results, motion, and fast-moving details. Small parts, like eyes, fingers, may change. MiniMax H3 block cache, T8, is an H3-specific caching method operating in a different way, but putting it simply, this node skips blocks while reusing their residuals created before. The start and end percent is the sampling window in which the cache is allowed to operate. The residual diff threshold controls how sensitive the cache is to changes. The cache compares the current block result with the previous one, and this comparison gives a residual difference score. If the difference is below the threshold, the model considers the state stable and reuses the cache. If the difference is above the threshold, it performs a full calculation. So the lower threshold is strict, resulting fewer cache hits and gives closer to native output. Higher threshold means more cache hits. The process becomes faster, but it also increases the chances of approximation. Max consecutive hits forces a complete refresh after a specified number of consecutive cache hits. So the default value 2 will force recalculation after 2 cache hits. In cache device, select CPU to save VRAM. If you have a larger VRAM, then select GPU to avoid transfer latency. Next is metric stride. This node uses the value that was previously calculated and stored in the cache. Before reusing the cached result, it samples the new state and compares it with the previous one. A stride of 1 checks every value, while a stride of 8 skips some values and checks roughly every 8th value. Increasing the stride reduces the amount of computation used for this comparison, but it can also affect the decision of reusing the cache by accepting it faster. You might wonder, if we are calculating the new state again to compare it with the previous cached state, why not just reuse the same value instead of comparing them? The important point is that this comparison is not being performed on the final video result. It is a relatively cheap decision step that answers the question, has the audio and video state changed enough that I need to run the remaining 49 transformer blocks again? Think of it like a car traveling on Highway 99. A few minutes ago, the car was on a different section of the same highway. Now, the car has moved to another section, but it is still traveling on the same highway. The new state is different, but not different enough to require everything to be recalculated. So the cached result can still be reused. Next, we have the MiniMax H3 low VRAM attention and MiniMax H3 chunk feed-forward nodes. Both of these are memory management nodes, not quality enhancement or caching nodes. These nodes are designed to let the model run at high resolutions or longer durations that might otherwise exceed your available VRAM. The attention normally creates large temporary GPU buffers. This low VRAM attention node reduces peak VRAM usage by processing the attention heads in smaller groups and freeing some temporary buffers sooner. The head chunks input controls how many groups the attention heads are divided into. A value of 1 means there is no head splitting, while 4 means the attention heads are split into 4 groups. The out-of-memory exception often happens when the video duration is long or the resolution is high. Increasing this value will split the work and avoid the memory exception. But every time the CPU orders the GPU to launch the next task, it also incurs a cost of CPU to GPU latency followed by memory allocation and switching latency. You should also make sure not to underutilize GPU cores. Split head into multiple small chunks won't give enough work to keep all GPU cores busy at full capacity. The other node to be used along with this node is the chunk feed-forward. The MiniMax H3 transformer contains large feed-forward layers, and this node splits the packed token sequence into smaller pieces, which means both the nodes work on different parts, and the input value in both the nodes are independent. The input name chunks is the number of pieces into which the token sequence is divided. The value 1 means no chunking, and higher the values, lower peak VRAM, but more CPU to GPU overhead, as explained before. The second input value is seek threshold. Chunking only begins when the packed token count exceeds this value. Leave it as it is for the H3 model. Both the nodes split work to avoid out-of-memory error. The way I think you should be using it is when turning up the video resolution and duration, let the chunk value be 2 and head chunks at 1. See if you get OOM. Then start increasing head chunks to find a value that works. Then check the GPU usage. If it is around 100%, then increase the chunk, make it 4. The attention nodes we saw before can be connected one after another. In case sole attention fails, the node before that will work. Check the program's output to see which attention node is being used.
Can I use Sage Attention and all 4 caching nodes together?
Sage makes attention faster. Caching skips repeated work. They are not 4 magic speed buttons. Test one attention method and one cache at a time. Same seed, same prompt. Otherwise, nothing means anything.
So that was it for this video. I hope you learned something new, and I wish you an excellent day.